It's my distinct pleasure now to introduce Carlo Scalo. He got his BS and MS degree back in Italy at Napoli in 2006 and 2008, and then a PhD in 2012 from Queen's University in Canada. And he has been at Purdue since 2014, and just recently promoted to associate professor. So Carlo's educational endeavors are interdisciplinary in nature. He is actually cutting across the whole mechanical engineering curriculum by involving dynamics, heat transfer, fluid mechanics, thermodynamics, acoustics, and controls, both with experimental and he is very talented and a dynamic individual, as you will see, conducting a creative and challenging research work in the areas of computational methods for compressible flows and energy systems modeling. His notable awards include an AFOSR Young Investigator Project in hypersonic transition, as well as an Army Research Office Young Investigator Award in large eddy simulation and vortex dynamics. Really looking forward what Carlo has to say as part of his presentation today. And Carlo, it's all yours. Thank you for doing this.
Thank you, Echo. I hope you guys can hear me.
Yep.
Thank you for the introduction. What I will do is, I'd say, cover the three main pillars of my research that I have, of my research portfolio that I have developed at Purdue, which are these three items that I mentioned here, as well as discussing a bit of what I've done in terms of teaching and my vision, if I may share that, on teaching needs at Purdue and outreach and so forth. So just diving immediately into the research part, I want to share with you what I've done for my PhD, which has nothing to do with what I'm doing as faculty. As a PhD student, I was faced with the challenge of modeling. I'm a fluid dynamicist, I do fluid mechanics, of modeling turbulent mixing in geophysical environments such as the ones that you're looking at here. This is the Baltic. This is a satellite image of the Baltic Sea, where you see all sorts of nutrients, pollutants, and many other quantities of geophysical relevance being mixed in the Baltic Sea. And obviously, this is in the realm of environmental fluid mechanics, and I was looking at turbulence in incompressible flows, such as water in this case. Well, I rushed through my PhD. I put my head down, pushed my publications out, and gained some knowledge and basic training in turbulent flows and computational prediction of these sort of flows. And I had the opportunity to start my postdoc at Stanford in 2012. And at that point, I changed topic completely. I went from environmental fluid mechanics to something more applicable to combustion systems and acoustics and highly compressible flow. What you see here is an image of a combustion chamber, which I've actually has been shared with me by Dr. Slabaugh at Purdue in the Zucro combustion labs. And so my focus shifted from environmental fluid dynamics to what happens to flow in chambers, such as a combustion chamber that you see here. The flow goes from left to right, and there's a flame that you can't see in this instance. And what happens to waves and flow as it's compressed, and it creates very high amplitude sound. These combustion chambers, if they're not designed well, they start to vibrate. The gas inside the combustion chamber starts to vibrate, and the combustion chamber might structurally give in and break down. And I've done quite a bit of theoretical work on nonlinear acoustics and high amplitude sound. And this is something that I started as a postdoc at Stanford, but midway through my tenure track, I was called upon, given my knowledge in turbulence, I was called upon solving this other problem, unrelated problem, but still involving turbulence and fluid dynamics. How do we model, and this is a separate topic and more on the hydrodynamic side, how do we model the interaction of high Reynolds number flows and vorticity in an environment such as this one. This is a very challenging problem. And so this started a new field of research, the second pillar of research in my group, which is vortex dynamics and turbulence. So the first pillar is nonlinear acoustics and highly compressible flow, if you want reactive flow. The second pillar is vortex dynamics and turbulence. This is work that was initially funded under an STTR grant. And just to skip ahead, what we have been doing is looking at very complicated theoretical, topologically complex vortex shapes. Imagine this is a trefoil vortex as a fundamental test case. And we have been devising numerical methods to very accurately model things like that, motivated by that helicopter landing on an aircraft carrier type of problem. And what is really challenging about flows like this, where you have vortices entangling and creating small patches of turbulence, is really realizing that wherever turbulence occurs, you have different flow physics than wherever turbulence doesn't occur. And so this led to contributions in Journal of Computational Physics, as well as Journal of Fluid Mechanics, where you see simulations, highly accurate simulations at very high Reynolds numbers. These need a supercomputer to be executed, and turbulence modeling associated with them. This is wonderful work carried out by one of my first postdocs, Jean-Baptiste Chapelier. He's now at ONERA in the French Aerospace Center in Paris. And this work led to the Young Investigator Award by the Army in vortex dynamics and turbulence modeling, which is now funding another postdoc, Xiran Zhao, who's doing wonderful work in adaptive mesh refinement and highly complicated numerical simulations of these complex vortex structures, which again are the fundamental equivalent of what the Navy was originally interested in, which is helicopters landing on an aircraft carrier. And so we're very excited about this work, and still under Army Young Investigator Award funding, we're carrying out a collaboration with physicists in Chicago, very nearby, on fundamental vortex dynamics problems. And so this is the second pillar of my research. I talked about acoustics, highly compressible flow in a combustion chamber, for example. Now I talked about turbulence and vortex dynamics, but these two combined, acoustics and turbulence, actually are the stepping stone for the third pillar of my research, which is high-speed boundary layers and high-speed flight. You might ask, why do acoustics and turbulence put together yield a brand new effort in my research group, which is high-speed flight? Well, it turns out that acoustic waves and turbulence do happen in very high-speed flight environments. And so this is a stock photo of what a very high-speed vehicle looks like. This is a vehicle that goes through the outer layers of the atmosphere. Well, it turns out that from a fundamental physics perspective, in the boundary layer, the flow attached to this vehicle exhibits very high frequency, very high amplitude waves that pound on the vehicle surface. So there goes your acoustics component of it. These waves break down into turbulence further later on in the vehicle or on the surface of the vehicle. So you have both aspects. You have acoustic waves breaking down into turbulence. And this is supporting these fundamental flow physics, or what we're investigating, what my group is investigating in the third, let's say the third effort or third pillar. And these are high fidelity simulations. These took more than maybe 4 years to figure out how to run. This is a flow at Mach 7.4. It's a flow, the flow goes from left to right, and it's a flow at more than 7 times the speed of sound. It's the simulations are the hardest simulations I've ever done in my life. And the leading student, Victor Sosa, is the one who's been carrying the weight of this. He's been doing a remarkable job. In the interest of time, I think I have maybe just no more than other 5 minutes. I may have gone a bit too fast. But in terms of teaching, I've been also a bit restless on that side. Eckert said energetic, and that's a very kind way to describe me. Restless might be a better adjective. And so I taught computational fluid dynamics at different levels. I taught at a 400 level as a technical elective, and I had so much fun. I recruited actually among the best students that are now in my lab from this 400 level course from Purdue. And very excited to have introduced this course. It's a technical elective, it's not a core course. Then there's a computational fluid dynamics course, 614, that had been taught in the past, but when I started, it had not been taught for 3 or 4 years maybe. And this was focused on structured grid, high order methods. I also taught a different course in computational fluid dynamics, 600 level, focused on unstructured grid, a bit more complicated geometries. Then I started a new course because I was bored and because I think it was very necessary, on computational fluid dynamic stability. So how to solve fluid dynamic problems by linearizing the governing equations and coming up with an eigenvalue problem to be solved numerically still. You can think of me as a computer junkie, as all of my students are as well. What I envision is actually computational education to be consolidated at Purdue. I think there's not enough right now. And so this is a bold suggestion, but I think numerical methods for engineering should be part of the core program of ME, aerospace, and of engineering in general. And so I would love to teach a course like that. Another itch to scratch that I have is teach yet another computational fluid dynamics course at a 600 level, focus on high-speed flow and compressible flow. Believe it or not, you need a different set of tools, a different set of knowledge to deal with highly compressible flow as opposed to low-speed flow. In terms of engagement and outreach, I started a NATO task force. NATO is a North Atlantic Treaty Organization. It's a workshop that brings together international experts in a given field. I have started a NATO task force. It's something I'm very proud of. It took a lot of grit to figure out and to initiate, but I'm the chair of a NATO task force in high-speed flight. And I'm also the proud founder of a startup that has received funding that is further increasing the scope of my fundamental and applied research. I can't say much about the startup, but what I can say is that it has an Italian boss and it's an American company. So I think with this, I can conclude my brief slides. Thank you.
Thank you very much, Carlo. Great work, great presentation, and appreciate the variety of topics that you tackle. So with that, I would like to open for question and answers. Please raise your hand if or hopefully you can unmute you, or the host will unmute you, or write a question in the chat room. Right?
I can read.
Yeah, I think there's a question. Why did you change your major halfway through your PhD?
Yeah, and there's a question before that too. But anyways, I'll answer that one too. Why did I change my major? Meaning, well, during my PhD, I worked in environmental fluid dynamics. I could have worked in topics that were maybe more exciting, but I put my head down. I finished my PhD, and I had an opportunity at Stanford to work in nonlinear acoustics and highly compressible flow, something I knew nothing about. And so the opportunity led to that change. And if it wasn't for that, my entire research portfolio is absolutely not based on my PhD. And so I reinvented myself because I had the opportunity to do so. And Alice Polly is saying, Canada represent. I did my PhD in Canada. I will forever miss how everything makes sense and everything is clean and linear in Canada. America is a land of a lot of mixing and turbulence, as my research is as well. But I have fond memories of Canada, and that's where I learned my basics in turbulence modeling and high performance computing. So I would say maybe it has not been that much of a change from my PhD, but definitely the topic is very different.
Okay, very good. You said you saw a second question. I don't know that I saw that.
I addressed it while addressing the question that you raised.
Very good, thank you. Okay, any other questions for Carlo?
Yes, Canada is very linear. I've never done taxes before in my life, and my first time doing taxes in Canada took 5 minutes, and I didn't need an accountant. So that's how linear the country is. Everything makes sense. Everything is I have a lot of very good friends back in Canada. So yes, I'd say Canada is very linear.
So do you see that question? Yeah, go ahead.
So what advice do you have for junior colleagues to find collaborators across Purdue? So Purdue is such a big school, and it carries out top tier research in almost any field that you can find or that you're interested in. So it is very easy to reach out and find people that can help you and that want to help you. 99% of Purdue faculty are very collaborative, and they do want to work with you, and they do want to increase their research scope working with new faculty. So absolutely do not hesitate. One advice I could give is maybe don't let yourself be distracted by maybe other people wanting to impose what they want to do on your research portfolio. Have a vision, pursue it, and then find people that can help you pursue that vision. And at Purdue, you will definitely be able to find always a person to help you for pretty much each and every one of your projects. So do not hesitate to reach out. Purdue is a top tier school, is a wonderful school. And so that's my advice.
Yeah, that's very good advice, Carlo. Actually, I would support that 100% from our own personal experience when I came as an assistant professor, but also now mentoring junior people, right? A very collaborative environment, and always willing to help our junior faculty to succeed. So definitely people should reach out. Thanks for the comment. Any other comments for Carlo? Arvin, how are we doing on time?
I think we're doing fine.
Good, good, outstanding. Okay, Alice Pauly has a question. Can we unmute her?
Looks like I don't get to take my video off anymore or turn my video on. I was going to ask the same question I asked Allison, which is, do you have a lesson about how to do this work that you have gained from your pre-tenure experience? Like, what is the one, like, here's how I now understand how to do this job sentence? Thank you.
Grit and vision pay off, regardless of the distractions that you might have around you, and the push and pull that you might feel around you that to distract you. If you have a vision, and if you have determination to pursue it, do it. I know it sounds like a fortune cookie type of statement, but grit shows the moment where you feel that everything is crumbling around you. That is something very important, to stay put and pursue your vision. I mean, do listen, obviously, to advice, and even if it's hard to hear. But one of my best accomplishments have been in specific fields or specific topics that I have been discouraged to pursue, and that's quite interesting. So if you have a vision, if your gut is telling you that something is important and has to be pursued, do it, because if you made it at Purdue, and if you're a professor at Purdue, if you're an assistant professor at Purdue, it probably means that you know what you're doing. So do stay strong in that sense, and it does pay off. And I think it did for me.
Great. Just received the message that we need to move on. Thank you, Carlo. And I hope everybody can give Carlo a hand virtually. So really appreciate it.